So when we were working in 2 dimensions, there are 2 main coordinate systems. There's rectangular and polar. Just a reminder, let's think about these in Desmos. So this is rectangular. It's the one you were working with most of your algebra and pre-calculus life. Everything's in nice grid with squares. And then polar, we learn about in, well, pre-calculus and then even more so in Calc 2, where everything is centered around the pole with the angles. Now, how do we work with 3 dimensions? So when we're in 3 dimensions with rectangular, it's kind of easy. I mean, we just added on another set of grids for another axis, and we just started thinking of everything in terms of cubes. Okay, wonderful. But that's not going to work for polar. So if you imagine that polar grid, how do we expand it to the 3rd dimension? And there are 2 ways that we do this, and that's how we've broken up this section. So there's cylindrical coordinates, which we're going to cover now in part A. And then there's spherical coordinates, which we will cover in part B. And they're related strongly to the polar coordinates. So they're the 3-dimensional equivalents of polar coordinates. That's how you have to think of them. But there's 2 different ways to do this. All right, so let's look at the cylindrical coordinate system. Now, the cylindrical coordinate system is basically taking the polar coordinates in one of the planes, right? So one of the coordinate planes, usually the XY plane, becomes that coordinate, that polar coordinates that we're used to looking at. But then the 3rd variable is vertical. So if you can imagine, you have your polar grid down here, right, going around and around and around in circles. And then what you do is you imagine that polar grid being taken up to a 3rd dimension. So you have your polar grid going around in circles at the base, and you expand it in a 3rd dimension. Right? That's the polar coordinate system, or excuse me, that's the cylindrical coordinate system. You build a cylinder out of the polar coordinate system. All right, and the way to do that is, this should look familiar, right? The same changes we made for polar, but your 3rd variable is just the 3rd variable, right? So all of these things are the case. This is how we converted between rectangular and polar, and we're just going to add that 3rd dimension. So if we do this, then if we do x as r cosine theta, y as r sine theta, and z, then the cylindrical coordinate system would be, and the order it goes in is r, theta, z. All right, that's the most common, but you can also do it in other directions. You could do r theta x or r theta y, depending on how you set up your 3rd dimension, right? Is your 3rd dimension z? It most often will be, but it does not have to be. All right, so let's think about a cylinder. So actually, there are several things that we just want to think about what they would look like and come up with some equations for them. So a circular cylinder, we all know what that looks like. Right? I just kind of drew one up above, but not as good as the one I'm about to draw. There we go. Right? So this is a circular cylinder. It's a circle on the bottom. X squared plus y squared is r squared. So r squared is c squared, and therefore r equals c. So if we establish r is equal to some constant, that's a cylinder with radius, well, it's a circular cylinder, radius c. And I just want to show you how I did this in Maple. So a cylinder plot is one of the ways that we can graph in cylindrical coordinates. And so I just said, hey, graph me 4, because that's r equals 4. It's assuming that r equals is what the general form of the equation is. And so when I say 4, it graphs me automatically a cylinder of radius 4. That's what it does, right? Okay. What about half planes? If y is equal to cx, so let's say we have this going on. This is your x, this is your y. If y is equal to cx, think about what that looks like. We know that that's coming out on a diagonal, right? So there's some diagonal here that's cx. It would come out from up here as well and would create this plane, right? I can make it go out longer so you can see it. It's sort of like a door, right? Hinging on the z-axis. Okay, so what would that be? If y is equal to cx, that means that y divided by x is equal to c. But y divided by x is the tangent of theta. So I know the tangent of theta is equal to c. So I know theta is equal to the arctangent of c, which is some constant k. And therefore, this would graph as theta equals k. So a vertical half plane has an equation that is theta equals a constant, some constant. Oh, and for the record, a circular cylinder has that as its equation. We're coming up with the equations for these in 3 dimensions. So a circular cylinder has r equals a constant. A vertical half plane has theta equals a constant. Vertical half planes are sort of like hinging around, if you imagine they're doors with the hinges at the z-axis, and they can spin around, right? Because of course theta is equal to some angle right in here. As a matter of fact, theta is right there. Right, there's theta. So theta is equal to k, right? You're establishing theta as a constant. All right, what about a horizontal plane? Z equals c. Well, a horizontal plane is sort of like a floating carpet, right? We've seen that before, right? When z is equal to some constant. But because z is equal to z, then the equation for that is actually z equals a constant. So horizontal planes work differently than vertical planes. Vertical planes are theta equals a constant. Horizontal planes are z equals a constant. All right, now what about cones? So the circular half cone, z is equal to c times the square root of x squared plus y squared. That is a cone that is centered at the origin, swooping around the z-axis, right? So here's your z-axis right here. That's what it is. Okay, so that would be z equals c times the square root of r squared, because x squared plus y squared is r squared. Therefore, z is equal to cr. And the way we work in polar is we tend to solve for r, or polar and cylindrical. So we tend to solve for r on these. So r is equal to z divided by some constant. Or if you want to think of that, that's 1 over c times z, and we generally like to write that as kz, where k is some constant. So you can write it as this way, or you can write it as this way. All of these ways are perfectly fine. And this one I could do in Maple. The horizontal planes and the vertical half planes are a little hard to draw in Maple because it's established as an r equals. So when you do cylinder plot, it's thinking you want the cylindrical coordinate system, and so it's hard to do theta equals because I really can't. I can only do r equals because that's assumed. So this is r equals, and I did z divided by 4, and you can see that it's a cone. Right? It's a cone. I'm going from 0 to 2 pi, so I'm going all the way around the cone. And then z I took from 0 to 2 for no good reason, just because I felt like it, but I could have gone as far up as I wanted to. Okay, and then the last one, we could see it was coming in the Maple file there, but it's a circular paraboloid. So a circular paraboloid is kind of a bowl shape, where the bottom is a parabola, kind of, if you look at it at the crossways. And then it creates this bowl shape here. I don't know why I made that dotted. You can see that inch. So then that would be z equals c times r squared. So that's the equation for that. Now, a lot of times that's weird. We don't usually solve for z equals. We have to here for the horizontal plane because we don't have any choice. So that works, but we could also solve this for r. So let's do that. So r squared is z over c, which we know means it's kz, right? K being 1 over c. Just depends on how you want to write your constant. And then r would be the square root of z over c, which is the square root of kz. All of those are fine, right? Or you could write that as, I don't know, I need some other constant. M square root of z, right? There you go. All of those work. The key is that you're doing the square root of z times a constant, right? The constant could be underneath the square root or outside the square root or under the square root in the denominator. It doesn't really matter. It's all constant. So the key is that it's some number times the square root of z. So of those, this one's probably the one we use the most often. But the other ones are all perfectly correct as well. All right, so let me show you that in Maple. Right here. So there's the paraboloid. So you can see the bottom forms a parabola, right? That's a parabola shape if you look at it crossways. And then I just had square root of z over 4. That's just how I put it in. So it just graphed a paraboloid. Simple as that. And again, cylinder plot is graphing in the cylindrical coordinate system. Let's take a moment and just do the first example where we're going to convert from rectangular coordinates to cylindrical coordinates, because that's going to use those definitions we just had. So remember, in rectangular coordinates, this is x, this is y, and this is z. And we want to convert them to cylindrical coordinates. So we need r, theta, and z. Well, the z is really easy. The z is 5. So half of our work is done. Well, a third of our work. All right, but how do we find r? R is x squared plus y squared equals r squared. So 1 squared plus negative 1 squared is 1 plus 1, which is 2. And that's r squared. So r is the square root of 2. We don't use negative r. We kind of ignore it. Technically, plus or minus is possible, but we're going to kind of ignore negative r unless we have a reason to use it for the particular problem that we're doing. All right, so we already know we've got square root of 2, and then we know we have 5. All we need is the theta, and life will be grand. Okay, so I figured out the r. Now theta. The tangent of theta is y over x. So that means that theta is the arctangent of y over x, which would be the arctangent in our case of negative 1 over 1. So we have to know what angle on the unit circle would have the tangent of negative 1. And keep in mind, we know what quadrant we're in. I mean, the x and the y are 1, negative 1. So we know we're actually over here, right there. So we know what angle that is, right? That's negative pi over 4. Or if you will, it's 7 pi over 4, whichever way you want to write it. I don't know if they gave us some limits for our thetas. They didn't. So let's just put it in here. We'll just make a note. So we'll say note 0 is less than or equal to theta, which is less than or equal to 2 pi. Right? Just like with polar coordinates, there's infinitely many angles that'll make this happen, because you can go backwards, negative pi over 4. You can go around positive 7 pi over 4, or you can keep going around and around and around and adding on 2 pi's. So it gets a little crazy. So usually we have some kind of note somewhere about we're only going to look in the first cycle. So that would make our angle 7 pi over 4. Okay, so 7 pi over 4. Boom. And that's because, of course, 7 pi over 4 has the tangent, well, it has sine and cosine are the same values, but they're opposite signs. And we know we're in that quadrant because of the 1 and the negative 1. All right, now let's convert from cylindrical to rectangular. So this is given to us as r, theta, and z. And again, we know the z already, so that's nice. Now remember, x is equal to r cosine theta. So that would be 2 times the cosine of pi over 3, which is 2. And of course, we all know the cosine of pi over 3 from pre-calculus. It's a half, or at least we should, right? So, and let me highlight the formulas we're using. So this is the formula we're using there. This is the formula we're using there. All right, so I know that it's 1. And then I know y is r sine theta. So that would be 2 sine of pi over 3. So that's 2 times the square root of 3 over 2, which is the square root of 3. So xyz, right, so this was r theta z for that one. This one's going to be xyz. So xyz is 1 square root of 3, 5. That's our solution. Let me just highlight this. That's the formula we were using. So the conversion's not too bad as long as you remember your polar coordinates and your unit circle. Then you should be golden.